We're excited to do a live fireside chat with Aparna and Yann. Yann LeCun is the VP and Chief AI Scientist at Meta and Silver Professor at NYU. Aparna is the VP of Engineering at Meta, responsible for all our data infrastructure. I want to remind you all, there will be a Q&A box at the bottom of your screen for this session. Please use it to ask Yann live questions. Thank you.
Hey, everyone. I hope that you're finding data at scale as exciting as I am. I'm delighted to be hosting today's fireside chat with a pioneer of AI. Today, we're exploring the impact of AI and ML on data systems. So it's only fitting that we're speaking to our very own Yann LeCun. Yann is Chief AI Scientist at Meta. He's the recipient of the 2018 Turing Award for conceptual and engineering breakthroughs that have made deep neural networks a critical component of computing. Yann, welcome to Data at Scale.
Well, it's a pleasure to be here. Thanks for having me.
Yann, there's so much to discuss, but I'd also like to welcome our audience to participate. So if you're watching and have relevant questions for us today, please drop them into the Q&A box that you see on your screen. We'll get to those if we have time towards the end of our chat. Yann, let's start off by getting to know you a little bit better. What led you to the field of AI? What led you to Meta? What does your current role as Chief AI Scientist mean?
Okay, so what led me to AI is a fascination for the mystery of intelligence. You know, what is intelligence? That's one of the biggest, most important scientific questions of our times, you know, together with what's the universe made of and what is life all about? You know, the next one is how does the brain work, or what is intelligence? So that was kind of a question that fascinated me, which is why I got into this field, you know, even when I was still an undergrad, and then, you know, started working on this, you know, during my PhD, and then sort of continued working on this. So that's the mystery of intelligence. And you know, intelligence requires learning, at least in the biological world. Every animal is capable of learning. So I think learning is an essential part of intelligence. How I ended up at Meta is that a little over 8 years ago, I was recruited by Mark Zuckerberg and Mike Schupfer, the CTO at the time, to essentially create a research activity in AI, because they knew that AI was going to be strategically important for the company. It wasn't clear exactly how at the time. And it turned out to actually be really crucially important for things like content moderation and various other things, integrity. So that's the story.
It's a fascinating story. So let me go right into the heart of some tough questions here. Like, how do you feel like AI is evolving in the future? Because some people claim that deep learning has hit a wall. Do you anticipate more AI winters? How do you see this field persisting, growing through these challenges?
Okay, so there is a bit of a historical point, which is that whenever there was an AI winter, it didn't mean that people stopped working on what it is they were working on, but it meant that people kind of changed their ambitions. And instead of claiming that they were working towards building intelligent machines, they were merely trying to solve an engineering problem. So there was a first wave of machine learning, you know, back in the 1950s with the perceptron and various other models until the 1960s. And when that field realized they were hitting a wall, what they did is that they changed the name of what they were doing. They told it, they instead of calling it, you know, machine intelligence or something like that, they called it statistical pattern recognition or adaptive filtering. It was the same techniques, but, you know, the name was changed. Same for kind of symbolic-based AI. You know, people, you know, started talking about, you know, path planning and you know, search and heuristic algorithms and things like this. And it became part of the computer science toolbox, you know, without the ambition of building intelligent machines or understanding intelligence. So now what's happening now is that we have a new set of tools with deep learning, which have had enormous success, you know, in the last decade or so in various applications. And this is going to remain part of the toolbox. So I don't think we're going to see a winter of the type that we've seen in the past. I think those things are going to be part of the toolbox. What we are working on at the moment, what I'm working on certainly, is like how to get to the next stage, how to get machines considerably more intelligent than the current state, using, getting them to learn like humans and animals, for example. And, we'll hit a winter if we don't make significant progress before the people who are funding all of this get tired of it.
Okay, so let's take that a step further. So 5-10 years into the future, I know there's a huge discussion, and we chatted a bit just before we got on this call. How do you feel like AI is going to change? Do you expect that it looks like a lot of the techniques today with just larger scale and compute? Or do you expect more fundamental changes? And I think this leads into what you were discussing in your blog post and in the post that you made about generalized intelligence. So you want to touch upon that and give us your opinion?
Yeah, for those of you who are watching who are interested, I made a post yesterday on Facebook, Twitter, and LinkedIn. It's the same post. There's different types of comments, but basically it's my vision for what necessary steps we need to clear to make progress towards let's call it human level AI. And a couple of months ago, we also published a blog post on the Facebook research blog that explains that in a bit more details. There's various talks on YouTube that I've given over the last 2 months that basically explain in sort of more technical term what I mean by all of this. But essentially, I think current methods that we use are very useful for the next step in AI, but not sufficient. So I think we need to have a certain number of conceptual breakthroughs to allow machines to learn essentially like animals and humans, and be able to, basically learn how the world works by observation, and thereby perhaps reach some level of common sense, which has completely eluded AI systems so far. So within the debate, there are people who say, we have all the techniques, it's just a matter of scaling them up. We have, transformers, we can train them on just about anything. And if you make them big enough, they were going to be able to learn everything. So there's people at DeepMind and Google who are kind of advocating this, people at OpenAI as well. I don't personally think that that's sufficient. I think we need other conceptual breakthroughs that we haven't gone through yet. There are people who say, let's just scale up reinforcement learning. Reward is enough. Okay, so there are people who claim this. I certainly don't think that's possible, at least not in how reinforcement learning is currently understood. And then there is kind of the contrarians who say, none of this is ever going to work. What characterizes human intelligence is the ability to do symbolic manipulation and reasoning and stuff like that. And you would have to hardwire some, specific circuits into your systems to reach human level intelligence. I don't believe in this at all either, because I think whatever architecture that we build will need to be compatible with gradient-based learning, which is what deep learning is all about. And symbolic manipulation really is essentially non-differentiable. So this may be getting into sort of kind of more technical things. But so essentially, I've been putting my bets on a concept called self-supervised learning, which would, if we were able to really kind of find general ways to do this, would allow machines to learn and understand how the world works by watching videos, by a minimal amount of interaction with the world. Basically kind of like babies learn when, in the first few months of life, they learn an enormous amount of background knowledge about the world.
So let's spend some more time in the self-supervised learning that you just touched upon. Can you give us a quick explanation of what it is and why you believe it's important to the future of AI?
Okay, so the one sentence definition of self-supervised learning is learning to fill in the blanks. Okay, so you have a piece of data. Think of it as a video, an image, a piece of text, a sequence of symbols, whatever it is, speech, doesn't matter what it is. And within, let's say it's a video, you show the machine a piece of that video, let's say the initial segment of that video, and you hide the rest, and you ask the machine to basically predict the rest. Okay, predict what's going to happen next in the video. And then you reveal what happens, and the machine adjusts itself to kind of refine its prediction. Okay, so that's one example. Another example, which is actually has been unbelievably successful in the context of natural language understanding is text completion, right? So you take a piece of text, you remove some percentage of the words by masking them, blanking them out, and then you train some gigantic neural net to predict the words that are missing. In the process of doing so, the system has to learn the structure of language and understand that if you say the cat chases the blank in the kitchen, the blank is probably a mouse or something like that, a small animal. Or maybe a laser spot. So that is kind of the type of understanding that those self-supervised learning systems can do. So this has worked astonishingly well for natural language understanding and for things like even protein structure prediction. The best systems that are able to predict the conformation of a protein actually are pre-trained using this idea of masked structure, prediction of masked filling in the blanks, essentially. But it hasn't so far worked nearly as well for images, for learning representations of images or learning from video, as I was describing before. And the reason is because video and images are much more complicated than text. It's maybe counterintuitive, but text is discrete. Videos and images are continuous, and that makes the problem much more difficult because we can't deal with the uncertainty in the prediction as well. The problem with predicting what's going to happen in the video is that many different things that are all plausible can happen. And if you ask a system to make one prediction, it cannot make a single prediction that will encompass all the possible plausible things that can happen. And so how to do this is the difficulty.
Interesting. So the kind of tying back to the theme of this event, the impact of AI and ML on data systems. What do you see as the most the biggest challenges you see over the next few years as we think about data and ML together? What are some takeaways for this group?
So I think this idea of self-supervised learning, I think, is playing an increasingly important role, and I think that role is going to get even more important in the future. So what we're going to see, my prediction for the near future is that a lot of machine learning systems will be pre-trained with unlabeled data using self-supervised learning methods. Okay, so they basically be trained to capture the essence of the data and learn good representations of the data that can be used subsequently as the input of a downstream task that would be supervised or something like that, right? So I think that protocol of self-supervised pre-training followed by a supervised phase will be increasingly prevalent, and it will reduce the requirement for labeled data in sort of all the problems that kind of data science and machine learning is based on. So I think that's a big trend. That kind of protocol has already revolutionized natural language understanding and translation, speech recognition to some extent, and then will probably revolutionize image recognition over the near future. There's quick progress in this area. And perhaps if we make enough progress, we'll allow to train our machines on video, which will allow machines to understand how the world works. And then when it comes time to training them to solve a particular problem, they will already be able to rely on all the background knowledge they've learned, from text or video or whatever it is. So we see that trend also, that we go from lots of small specialized models, each of them constructed and trained for a particular task. The direction of history is that we're getting bigger and bigger models that are more and more general. So it used to be, for example, that at Meta, at Facebook, we had a translation system, right? We had translation system to translate, French into English, English to French, and German into Spanish, and blah, 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 and all the pairs, right? And we had a separate neural net for every pair and every direction. Now what we have is one giant, enormous neural net that does everything. Same for speech recognition. We used to have separate speech recognition systems for every language, and perhaps even every accent of every language, and even a separate model for male and female voices and for children. Now we have one giant big model that does everything, every language in the world. Hundreds of languages, not every language in the world, but hundreds of languages. And so same for image recognition. We used to have half a dozen different neural nets doing image recognition on Instagram and Facebook. Now we basically have one gigantic one. So we're going to see that trend of sort of consolidation of sort of more general models that are pre-trained, self-supervised, and then fine-tuned for every task that we need.
So interesting. There's a lot of conversation around sort of, we talk about models, like what about mathematical breakthroughs? Are we a few mathematical breakthroughs away towards achieving some of these bigger, loftier goals that we have?
So I think that there's going to be a need for mathematical breakthroughs. One of the things I've been advocating is so there's two pillars in machine learning that the machine learning community has been sort of very proud of, or at least relying on for a lot of work. And one of them is probabilistic modeling. And the second one is generative model. So a generative model is something, if you want a system that predicts videos, you show it an initial segment of a video, you train it to predict the next segment of that video, and it has to predict every pixels in that next segment of the video, right? That's called a generative model. And probabilistic modeling is the idea that you don't predict a single video, you predict a probability distribution over possible videos. Here's the problem. We don't know how to properly parameterize a probability distribution over all possible videos. We just don't know how to do it. We know how to do it for text. Like I can train a neural net to produce a distribution over the set of all possible words in the dictionary. So I can, do probabilistic generative models for text. I don't know how to do it. Nobody knows really how to do it for images. So I'm advocating for two things. One is abandon the idea that you need to do probabilistic modeling. And so I'm advocating for a kind of a new theoretical framework called energy-based models, which basically eliminates the sort of tractability difficulty that we have with probabilistic modeling. And the second thing I'm advocating is something called joint embedding architecture. So these are non-generative models, which basically, instead of training a machine to predict the next segment of the video, there's so many details in the video that are so difficult to predict. Like, we could be watching a scene, outside with the landscape, and there's, trees in the landscape, and there is a pond, and there is wind. So the leaves in the trees are moving, and the pond is, has ripples on it. And all of this is basically impossible to predict. It's kind of, highly noisy and chaotic. So you can't really predict. If you train a system to do video prediction, it has to predict every pixel. It can't predict all of this, right?
Yeah.
So basically what I'm advocating is something called a joint embedding architecture, which would take the segment you're supposed to predict and then encode it and eliminate all the information you cannot predict. So I'm basically advocating for doing prediction, but doing prediction in an abstract representation space where all the details that are irrelevant are being eliminated from the observation.
That's super interesting. We're seeing a question from the audience. I'm going to just take a break and go to the audience questions. This question is more about the scale of data and the scale of compute for AI, like particularly with self-supervised learning. And you talked about how labeled data is actually going to look very different in this new world. But how do you see it impacting the scale of data and the use of compute for AI? Is that going to dramatically change with supervised learning?
Well, what things like emergence of self-supervised learning allows you to do is use unlabeled data in massive amounts to pre-train your model so that when you need to train it for a particular task, you don't require as much labeled data, right? So, the experiments now in image recognition, for example, is that you pre-train a system on maybe 1 billion images from Instagram or something like that, randomly picked, and it learns to represent images. And then when it comes time to train the system to actually recognize objects, give them names or classify them into categories, you only need a few samples per category, and it works pretty well. So that's kind of the future. So in terms of data, I think we're going to see a trend where with, an increase in amount of data, sort of unlabeled data that is collected, and possibly a decrease in the amount of labeled data, or at least the possibility to apply machine learning to a wider set of problems for which it is not practical to collect a lot of label data. A good example of this is medical imaging and things of that type. But of course, there is a lot of domains where, in the long tail, where you just not doable to collect too much data.
Okay, so here's an interesting question from the audience. What implications might have quantum computing to the field of AI?
Okay, that's an interesting question. So my hunch, my opinion, which may be wrong, is very probably zero impact in the short term, and probably also in the medium term. The reason being that there is no demonstrable capability of quantum computing that is likely to appear in the near future that would make a significant difference for any machine learning problem. There's one small exception, which kind of made me change my mind a little bit about quantum computing recently, and it's things like similarity search. So it turns out there are efficient quantum algorithms for finding, let's say you have a long list of vectors and you have a query vector and you want to return the vectors that are closest to that query vector, which, by the way, is an operation that at Meta we use all the time for all kinds of stuff. Also an operation that is used in large-scale language models and transformers. That operation turns out to be doable efficiently with a particular type of quantum computer. And it's a particular type of quantum computer that may become practical earlier than the more serious type, because the more serious type requires things like quantum error correction and robustness, which nobody knows how to do.
Interesting. What's your opinion on large models? Is the next question. Transformers clearly being one of the emerging trends. I'll leave it with that.
Well, transformers are a great idea. They have an interesting property, which is that they're basically very large scale associative memories, right? So, I mean, the sort of multi-head attention kind of module, you can think of it as an associative memory module, which you can think of as kind of a type of universal approximator. The other property that transformer has is that it's equivariant to permutation. So you feed it with a bunch of tokens at the input, and you get an output, which basically is a number of vectors, the same number as the number of input tokens, which also themselves are vectors. If you permute the input vectors, the output will be permuted, but otherwise unchanged. So that's an interesting property, because it means that if you're doing some sort of reasoning or computation that depends on the relationship between objects, but does not depend on the order of the object, then a transformer will actually give you something really interesting. And it can establish dynamically kind of connections, kind of dynamically reroute the graph of connection in a neural net. So you can think of it as sort of a dynamically configurable neural net, which is sort of a really interesting thing to do. So it can learn fast because it's an associative memory. It has a high memory capacity because it's a bunch of associative memories that are connected with each other. In that sense, it's very very interesting. So there's been sort of astonishing results for large scale language models, like the GPT-123 or the latest model from our colleagues at FAIR, OPT 175B, which is basically an open source version of a large language model that is in open access as well. I mean, the smaller models are open access. For the big one, you need to ask permission, but it's still pretty easy. So I mean, those are pretty astonishing. I don't think they are the ultimate answer. So I don't think we're going to reach what people, what I would consider human level intelligence by just scaling up transformers and training them on more text. I think there is a lot more to human knowledge than what is present in written text. So I think we're going to need. I'm sort of a believer in grounded AI, if you want. So the fact that most of the knowledge that humans and animals have is non-linguistic, is basically learned from everyday experience with the real world. Which is much richer in terms of information and environment than any text. Text is a very low bandwidth medium. So I think to reach human level AI, we need systems that can learn from images, video, as well as text and speech and things like that. So models like Gato, which is a very recent model produced by our friends at DeepMind, goes in that direction, but I don't think it has the sufficient components. So some people have been like Nando de Freitas from DeepMind has been saying like we just need to scale up Gato and now that's the end of it. I'm skeptical. I don't think that's the case. I think we need a couple more elements.
So this is interesting. Can I go back to something we were talking about before we started this live session? One of the things I was asking you, and this is just, for all of us who are enjoying this phase of like AI in our lives, what do we expect to see in our lifetime in terms of actual applications that, we can count on in terms of the pace of research that you're seeing? Like, do I expect robots cleaning my dishes, doing my cooking? Where do we draw the, like, what do you think in this generation that we will see?
Right. Okay. So there is a bunch of problems that we could consider AI complete. So AI complete just means that you would require a machine that has essentially human level intelligence to be able to solve them. And for all of those applications that we may consider as AI complete, there is probably another solution to them, which basically relies on brute force engineering, essentially. So a good example of this is level 5 autonomous driving, so completely autonomous driving. I think the first completely autonomous driving systems we will see will rely on, more sensors than just cameras. They'll use LiDAR and, radars and everything. And they will rely on a lot of really careful engineering, where every street is mapped and, everything is, there's a lot of sources of information. Maybe cars talk to each other, through 5G radio or whatever. Okay, so there will be a highly engineered solution first, but then eventually, level 5 autonomous systems will use a type of autonomous AI that I kind of alluded to earlier, that will be capable of learning how the world works by observation. And, which will explain, how is it that any teenager can learn to drive a car in about 20 hours of practice, hardly with hardly any accidents, right? Whereas, our best machine learning system, even with millions of hours of training in simulation, are not capable of this today. So that's, one of those sort of AI complete system. Now, the other type of applications we might want in the future for our everyday life is intelligent virtual assistants that will live in our augmented reality glasses and help us in our daily lives. I don't know if any of you in the audience has seen the movie, the Spike Jonze movie, Her, from about 10 years ago. And that's kind of, a good depiction of the interaction that people might have with intelligent virtual assistant, when they're, AR glasses or something like that. So for that, we need something like, ultimately human level intelligence, because our virtual assistant will have to understand the world to the same extent that humans do. Then the last thing would maybe domestic robots, right? We'd like a robot that basically lives in our house and takes care of everything. And it's the same. Ultimately, that's an AI complete problem, and it may not appear in a practical term until we make this next quantum leap in AI and have systems that can learn how the world works.
Wow, this is a fascinating conversation. Yann, we're almost out of time. We have about a minute or two left. Is there anything that you'd like to share, final thoughts with the audience?
Well, what I want to say is that the progress in AI has been kind of astonishing over the last few years. We're still very far from human level intelligence. We need to come up with some new concepts, new ideas that will take us there. It may take 2 years, 5 years, 10 years, 20 years for the next breakthrough. It's not clear. There's a bunch of obstacles to clear to get to machines to learn like humans and animals. We can see the first one. I think the way to climb that first obstacle and clear it is based on self-supervised learning, energy-based models, joint embedding architectures that I mentioned earlier. And I would refer to my blog post and my recent talks about this. But I'm really very excited about the future. So, there were certain periods, like, back in the old days when I started working with convolutional nets, I was super excited about the possibilities of what we could do with, backprop neural nets and convolutional nets. And then sort of excitation kind of died down a little bit because, we realized we needed a lot of data and that wasn't really available until the internet took off.
Yeah.
And now there's sort of a new period of excitement and acceleration in progress, partly because a lot of people are interested in it. There is a lot of investment and, et cetera. So I'm very optimistic about the future and very excited in similar ways that I was, back 35 years ago.
That is fantastic. It was super cool to hear you talk, Yann, and thank you everybody for tuning into this fireside chat with Yann LeCun here at Data at Scale. Thank you, and hope you have a good rest of the conference.
Thank you so much.